Hello and welcome. In the last class, we were discussing the uncountability of open interval 0, 1 in the set of all real numbers. The technique we use to establish the uncountability is known as Cantor's diagonalization method. In Cantor's diagonalization method, we initially assume that there is possibly a 1, 1 onto function from the set of all natural numbers to open interval 0, 1, and using that function, we constructed a real number in the open interval 0, 1 in such a way that that real number doesn't look like any of f of 1, f of 2, f of 3, etc. Now we are going to see a strange fact about decimal representation of real numbers, and this strange fact probably tells us that there is some problem with the proof that we gave in the last session. Therefore, we need to rectify the proof that we gave for verifying that open interval 0, 1 is uncountable. We are going to do that now. So this is the question with which we are starting. Is decimal representation of real numbers unique? One possible example should reveal that the answer is actually no. So consider x equal to the real number 0.5 and y to be the real number 0.4999, etc., not terminating, and nines are keeping on going like that. Now suppose that we consider 10y, and this is nothing but 4.999, etc. Now if we consider 100y, this is going to be equal to 49.999, etc. If we take the difference 100y minus 10y, we get this is equal to 49.99, etc., 4.99, etc. Therefore the decimal part will be completely removed, so we will be getting 45 here, and this is 90y is equal to 45, or y equal to 1 by 2, which is nothing but 0.5. So we started with y equal to 0.499, etc., x equal to 0.5. Now we get y is actually equal to x, but x and y look to be somewhat different in their decimal representation, but they are actually the same. Therefore 0.5 has at least two decimal representations. What are the representations? One is 0.5 itself, and the other representation is 0.4999, etc. Okay, now we come back to the Cantor's diagonalization method, the proof that we gave in the last session. So the proof that we gave is the following. Proof for uncountability of 0, 1 using Cantor's diagonalization method is the following. Suppose f from set of all natural numbers to open interval 0, 1, suppose that this is 1, 1 onto. So we listed f of 1, we listed like 0.a11, a12, a13, etc. f of 2 we constructed to be, we wrote to be 0.a21, a22, a23, etc. And we will write one more. F of 3 we wrote to be 0.a31, a32, a33, etc. And the diagonalization method, we are considering this a11, we are considering this a22, we consider here the diagonal element A33, etc. We are considering these elements, and we constructed a new number So using these diagonal numbers, diagonal entries, we constructed a new number in the following way. We wrote y equal to 0.y1, y2, y3, etc. And we define y1 in the following way. y1 is an integer, a digit in D equal to 0, 1, etc. 9. But y1 not equal to a11, or precisely we took y1 to be from D minus a11, and after that y2 we define to be D, this is set a11, y2 from a22, etc. following like this, yi in general from D minus aii. Now the problem comes because of the non-uniqueness of decimal representation of a real number is the following. Suppose that the number y is nothing but this is equal to 0.4999, etc. We don't know what we exactly constructed. We constructed randomly choosing y1, y2, etc. from D, but yi is not equal to aii. That's the only condition. Suppose that the number y is this, and suppose sum f of I is equal to 0.5, then y look different from f of I, but they are indeed the same. So we have not actually constructed in that case a new number that is different from f of I possibly. So it is possible the constructed phi is equal to some f of I or y equal to f of I. So the proof is not therefore complete. So the problem here is that we completed the proof. We thought that the proof is complete because we assumed that the decimal representation is unique, and we constructed a number which is not having the same decimal representation as that of this f of i's, and therefore we assume that that's a new number. But it is possible that the number we constructed is 0.499, etc., and one of these f of I is 0.5. Therefore these two numbers definitely look different, but they are not actually different. They represent the same real number. So now the question is to rectify this. Probably we can assume that we can put some condition on, extra condition on this y1, y2, etc. We may probably say that y1 is not equal to 0, y1 is not equal to 9, because here there is a problem that if we are having 999, etc., and if you are having 0, 0, 0, 0.5 is nothing but 0.5000, etc. So if we try to define yi in such a way that yi is in D minus aii, at the same time yi is not equal to 0, yi is not equal to 9, then probably we can complete the proof, fill in the gap. But still there is one more question. How can we say that this is the only possible non-unique way of writing a decimal number? If we are sure that these are the only two possible representations, then we can safely avoid 0 and 9 and we can construct a y. But now the question remaining is, what types of real numbers have non-unique representation? How many representations a real number may have, and how to find all these representations? We will try to answer all these questions now. The question we are going to discuss is the following. If x and y are the representations of same real number, and if they look different, decimal representation we should write. If they look different, how do they actually look? If they look different, how do they look? So we want to know exactly how different decimal representations look like, or what is the difference, or what is the similarity between the decimal representations, two decimal representations, if at all there exists, of two real numbers. And we want to see that the number of decimal representations a real number can have is 2 or more, or it is just 1. Okay. Suppose that the real numbers is already given for us, x and y. X and y are the decimal representations. So x has a representation in the following form. So some integer part it has, decimal part it has. After that, the part after the decimal point it's there. Y also has such a representation. This is integer part, this is the decimal part, this is integer part, this is the decimal part. Now x will be having several digits in that, like x1, x2, x3, etc. Several digits after the decimal point also, before the decimal point also. Y also will be having several digits before and after the decimal point probably. So we are going to assume that, we are going to suppose that the difference between them starts at, suppose that x is having x1, x2, etc. and goes on like that, and y is having digits x, y1, y2, etc. like that. Suppose that till some yn, till some natural number n, the digits are the same and the difference starts from that particular n onwards. Suppose x has digits x1, x2, x3, etc. and y has digits y1, y2, y3, etc. in their decimal representation. Now we are going to assume that the difference in the decimal representation starts at some natural number n. For example, it may start from the very first number onwards, very first of x1, y1 onwards. Also the difference may start, we don't know. Suppose till n, the digits xi and yi are the same. That is, x1 equal to y1, x2 equal to y2, and one more, till n, which is a natural number, the digits are the same, and at n plus 1 they differ. Suppose, so x2 equal to y2, etc. xn equal to yn, and xn plus 1 equal to yn plus, xn plus 1 not equal to yn plus 1. Suppose that this is the case. That means till yn, till n, till xn and yn, the digits are the same and the difference starts from xn plus 1, yn plus 1 onwards. Okay, so Therefore, xn plus 1 and yn plus 1 are different, so we may assume without any loss of generality that yn plus 1 is greater than xn plus 1. So without loss of generality, assume that yn plus 1 is greater than xn plus 1. So that means that yn plus 1 is at least xn plus 1 plus 1. If we take a clue from the first example that we saw, here we have the number 0.5 and 0 everywhere else. So here in this example, the difference starts, this is x1, this is x2, this is y1, this is y2. So y1 and x1 are the same, y2 and x2 are different, therefore the difference starts with x2 and y2. And we can see that in this example, this x2 equal to 5 and that is greater than y2. But one important observation is that x2 and y2 differ exactly by 1. So here also we can probably ask that question. So can we say that yn plus 1 and xn plus 1 differ by just 1? So the question is the following. Can we say that yn plus 1 differs from xn plus 1 by exactly 1? Suppose that this is not the case, then what is the next possibility? Then yn plus 1 will be greater than xn plus 1 plus 1, or yn plus 1 is going to be at least xn plus 1 plus 2. Suppose not, then yn plus 1 is going to be greater than or equal to xn plus 1 plus 2. For example, we may consider the following two numbers, 10.52375 etc., something like that randomly, and then 10.53 or 52. Suppose that the difference is starting from this 3, and this is our x and this is our y. This is our x, this is our y. So in this case we have 3 here, and we want y. This difference is starting from this is y1, y2, y3, y4. Difference is starting from y5, and suppose that this is at least 5, and so on like that. So we have 5 and 3. If we the place value of this is 10 to the power minus 1, minus 2, minus 3. So the place value is minus 3. So here suppose that the place value of yn plus 1 and so of xn plus 1 also. Suppose that the place value of yn plus 1 and xn plus 1 are both 10 to the power m. Suppose we don't know whether it is negative or positive, where m belongs to the set of all integers. Suppose that this is the place value of the digit in x and y, where the difference in the representation occurs for the first time. So we are assuming that the place value is 10 raised to m. Here, if you look at the difference between these two, we can see that 1, 1, 0, 0, 5, 5, 2, 2 all are the same, and now the difference is in 5 and 3. Therefore we can say that the difference is going to be at most 5 minus, this is not at most, this is going to be, the difference is 2 here, and 2 into 10 raised to minus 3 is going to be the difference between these two. But remember that here there are something more, and here also there are something more. Therefore the difference is not going to be 2 into 10 raised to minus 3, but it is not going to be less than 1 into 10 raised to minus 3 also. So we will explain through one more example. We'll just see, not otherwise we will use the same example and we'll try to explain. So the argument is the following. So y minus x is going to be greater than or equal to 10 raised to m is the position value greater than or equal to 1 into 10 raised to m? That is definitely greater than 0. Therefore, y is not equal to x. This is the conclusion we want to make if the decimal digit where the difference is occurring for the first time, if they do not differ by 1, if they differ by more than 1, this is the problem that's going to happen. Okay, we will try to see using this same example. We have 10.52 x is equal to 10.52. What is the next number? 375 etc. and y equal to 10.525. Y equal to 10.525, maybe something like that. After that 3 and 5 differ, so y minus 6 is equal to 10, 10, 5, 5, everything gone. So this is going to be 5 0. Or otherwise, for the simplification, where is this change happening? 1, 2, 3. Okay, we will take 10 to the power 3 for somewhat simplicity. So this is going to be 10, 5, 2, 3.75 etc. minus 10, 5, 2, 5 point something. So the difference is going to be, see, here we have 10523.75, here we have 10525 point etc. So we would have taken y minus 6. This is not correct. This is 5, 2, 5 etc. That is 5, 2, 5 dot, we don't know what it is after that. Here it is 10523.75 extra. So the difference between these two, 10525, 10523, the difference is here 25, 23. It's going to be something of the order of 2, but we don't know. There are something else remaining, so the difference is at least 1. So this is going to be greater than or equal to 1, or y minus x is going to be greater than or equal to 1 into 10 raised to minus 3. This is what precisely we are saying here. So this is not possible because y will not be equal to x. Therefore y n plus 1 must be equal to x n plus 1 plus 1. This is the first observation we have. Repeating the argument once again, what we are seeing here is 10525 point something minus 10523 point something. The difference is at least 1 because the last digits 5 and 3 differ by 2. Therefore the difference is going to be at least 1. It is not going to be anything less than 1. It is at least 1. Okay. So we have at the n plus 1th position where the change is happening for the first time, one number differs from the other by exactly 1. See, from this example we can see that this is somewhat what we have seen just now. 0, 0, they are same. 5, 4. Therefore difference is happening in the second position here at x2 at 5, 2, and at that position one of them differs from the other by exactly 1. Okay, now we are going to see what happens to the remaining digits in the representations of x and y. Okay, now what about the remaining digits yn plus 2, xn plus 2, etc. This is what we are going to see now. If you take the cue from the previous example, we may probably think that yn plus 2 is going to be equal to 0 and xn plus 2 is going to be equal to 9. Of course, yn plus 2, xn plus 2 are all from yn plus 2, xn plus 2. They are all digits and therefore they all belong to 0, 1, etc. 9. But what we want or we guess that yn plus 2 which is larger, that will be having 0 in that place, and xn plus 2 which is smaller, yn plus 1 is larger, not yn plus 2. Yn plus 1 is larger, xn plus 1 is smaller, and from yn plus n plus 2th position onwards, y will be having 0 and x will be having 9. This is what we guess. So suppose that this is not so. Suppose it is not so. That means either one of these possibilities, either yn plus 2 is not equal to 0, or yn plus 2 n plus 2 is not equal to 0, or xn plus 2 is not equal to 9. That is yn plus 2 greater than or equal to 1, or xn plus 2 greater than or equal to, this is less than or equal to 8. Suppose that this is the possibility we have. So the question now we are going to discuss is the following. If the decimal representation of a real number is not unique, how many representations it can have? That is the first question that we are going to ask. Now after that, how to find different representations of a real number in case it has multiple decimal representations. So these are the two questions that we are going to ask. If the decimal representation of a real number is not unique, then how many representations it can have? So if the representation is not unique, it means that definitely there exists at least 2. And can there exist more than 2? That is one question. And in case there are more than one representations of a real number, how to find out all these representations? These are the two questions that we are going to ask and discuss now. Suppose that we consider a real number with more than one decimal representation, and suppose that in first representation the digits are marked by represented by x1, x2, etc., and in the second representation we denote the decimal digits by y1, y2, etc. Therefore, suppose a real number has two representations, in fact decimal representations, two decimal representations, one consisting of digits x1, x2, x3, etc., and of course there is somewhere decimal point is appearing, we don't know exactly where it is. The other representation is, this is the first representation. Suppose that we have another representation y1, y2, y3, etc. Definitely there is a decimal point appearing somewhere. Now it can happen that x1 and y1 are same, x2 and y2 are same, and the difference in the representation starts at x3 and therefore at y3. So we are going to look at the smallest n where the difference is going to start. Okay, therefore our next job is to find out the smallest n where xn and yn start differing. Let n natural number be the least such that xn not equal to yn. That means that x1 and y1 are same, x1, y1 same, x2, y2 same, etc. xn minus 1, yn minus 1 equal, but xn not equal to yn. N is the least natural number satisfying xn not equal to yn. So we are choosing such an xn, such a yn. and till that x and yn, just before up to that x and yn, all the digits in both these representations are exactly the same. Okay, so we have x1, x2, x1, y1 equal to y1, x2 equal to y2, etc. All these things are equal. If you take a cue from the previous example that we already have, we have seen here that if we consider the real number with representation 0.5 and 0.499, etc. So if we try to fit these x and y into our present situation, we have x1 equal to 0, y1 equal to 0, x2 equal to 5 and y2 equal to 4. So we can see that the difference in this particular case starts at x2, y2, and in this particular case we have x2 equal to y2 minus 1, or y2 plus 1 is equal to x2. So the next question probably we will want to ask is, is this phenomenon going to be the same for all multiple represented real numbers? That means wherever the difference between the representation start, the difference between the digits is exactly 1. So now we are going to see that. So next question is, can we say that the difference between xn and yn is exactly 1? This is the next question we are asking. So what we want to say is xn going to be equal to yn plus 1? That is modulus of xn minus yn less than 1 is the modulus of xn minus yn is equal to 1 is the actual thing we had to write. But without loss of generality, we may assume that if xn and yn are different, xn is going to be greater than yn, or yn is going to be greater than xn. So without loss of generality, assume that xn is greater than yn. So the question is xn equal to yn plus 1 exact? Suppose this is not true, that is xn equal to yn plus 1 is not true, but we know that xn is greater than yn. Therefore xn not equal to yn plus 1 means xn is more than yn plus 1, or xn is yn plus 2, yn plus 3, yn plus 4, etc. If this is not true, then xn is greater than or equal to yn plus 2. So it can be yn plus 2 here, not like this, yn plus 2. So xn can be equal to yn plus 2 or yn plus 3, etc. All these possibilities are there. If we assume that it is not equal to yn plus 1. Note that in the decimal representation, every digit has a place value or position value which is a power of 10. In decimal representation, every digit has a place value that is a power of 10. Now for this xn and yn, let 10 raised to m is the position value or place value of xn and yn. Okay, we will see this using one example. So the example is the following. So consider the following two real numbers. We take 13.425 etc. Okay, we will probably write it in some distance, 13.425 etc. and 13.42. So here we want etc. 4 to 5, etc. Now suppose that this is our x. So this is x1, this is x2, this is x3, this is x4, and similarly this is y1, y2, y3, y4, and the change is occurring at, suppose this is y5, and change is occurring at y5. Therefore our 10 raised to m is equal to 10 raised to, this is 10 raised to minus 1, 10 raised to minus 2, 10 raised to minus 3. Therefore 10 raised to m is 10 raised to minus 3. That is the place value of y5 and x5. So this is x5 and we don't know what exactly this is. Definitely this is going to be what according to what we assume here. See, here we have xn is greater than or equal to yn plus 2, yn is y5, yn equal to y5 equal to 5. Therefore x5 is going to be 7, 8 or 9. These are the possibilities. Therefore suppose we take the difference between these two numbers. Suppose we call this to be equal to y. This is equal to x. Suppose we call this representation to be x and this representation to be y. And if we take, we have already assumed that this is more. X is this particular digit in this digit is going to be x5 is going to be greater than y5. So we can probably subtract y from x. X minus y. Now we are going to see this in this case 13.42. we don't know what it is exactly, so this is x5, x6, etc. minus 13.425 y6, etc. So the difference is minimum when we have the least possible value for x5. But what is the least possible value for x5? We have already assumed that x5 and y5 differ by at least 2. Therefore x5 is going to be at least 2 more than y5. Therefore x5 is at least 7. Okay, so we can write in this case, okay, we will just move everything to the left side. Now the least possible value occurs when x5 is the least possible. So this is going to be greater than or equal to 13.42. What is the least possible value? At least 2 more than 5, which is 7, x6, etc. minus 13.425 y6, etc. Now the difference between these two is going to be 0.007 minus 5 is going to be 2, but we don't have 7 and 2. We have actually suppose that this is 7 1, suppose that this is 5 5, so we will be having 1 5, not 2. So what we can say is at most that this is going to be greater than or equal to 0.001, and this is equal to 10 raised to minus 3, where 10 raised to minus 3 is the position where the change occurs for the first time, where the difference in x and y occurs for the first time. So if you look at the general case, here we have 10 raised to m is the place value of xn and yn, where the change occurs for the first time, where the difference in xn and yn occurs for the first time, and xn is greater than or equal to yn plus 2. So exactly the same situation as in this case. Here xn is x5, that is 7, 8 or 9, yn is y5, that is 5, the difference is at least 2, and we have taken the difference in such a way that the difference is the minimum, and the minimum difference is going to be greater than or equal to 0.001, which is 10 raised to minus 3. Therefore in the general case we have, if xn greater than or equal to yn plus 2, then x minus y is going to be greater than or equal to 10 raised to minus m, that is greater than 0. Therefore x is not equal to y. But this is not possible because x and y are the decimal representations of the same number, and therefore they have to be the same. So what we assumed is wrong. What is your assumption? we assume that xn greater than or equal to yn plus 2. That is wrong. But at the same time, xn is greater than yn. Therefore, xn must be equal to yn plus 1. Therefore, xn greater than or equal to yn plus 2 is wrong, or since xn greater than yn, xn must be equal to yn plus 1. So this actually justifies our previous example. What was the previous example? We have seen that 0.5, 0.499, etc. The difference is starting from this position 5 and here it is 4. So we have here 5, here it is 4, and therefore they differ exactly by 1. Next question is, what about the remaining places? So we will initially ask, we have xn here, what about xn plus 1 and yn plus 1? Now, what about xn plus 1 and yn plus 1? This is the question now we have. And once again, going back to our previous example, we have here it is x equal to 0.5, which is nothing but 0.5, 0, 0, 0, etc. and y is equal to 0.4999, etc. Therefore, we can probably try to see that x has at the remaining positions everything equal to 0 and y has at the remaining positions everything equal to 9. Okay, so we are trying to see the following. We are trying to see if yn plus this, if this is going to be true. So we are trying to see the following, that xn plus 1 equal to 0, and if we don't know whether it is true, and yn plus 1 equal to 9. Okay, suppose that this is not so. Suppose this is not true, that is they are all digits, decimal digits. Therefore, suppose that xn is greater than or equal to 1, not xn plus 1 is greater than or equal to 1, or yn plus 1 is less than or equal to 8. Suppose that this is the case. Okay, now once again we take the help of the previous. In the previous example, we have x that this the first number is 13.42, not 7. We know that this y5 and x5 differ by exactly 1. Therefore, this first number is 13.426x6. So the first number is 13.426x6, 13.426x6, etc. minus what is the second number? 13.42y6, 13.425y6. Now the difference is going to be the least when we have x6 the least and y6 the most. So this is going to be 13.426. What is the least possible value of x6? Here it is equal to 1 minus, sorry, this is continuing, x7, etc. minus 13.425. What is the least possible value of y6? Here we have assumed that either xn plus 1 has to be greater than or equal to 1, that is x6 has to be greater than or equal to 1, or y6 has to be greater than less than or equal to 8. So if we choose x6 to be greater than or equal to 1, we can choose y6 to be even equal to 9. Okay, there is no problem because this is an OR. So we can choose y6 to be equal to 9, and if we choose y6 to be equal to 9, we have this is 9, y7, etc. So this difference is greater than or equal to. Now think of these two numbers, ignoring this 13.4261, etc. You just forget about all these digits and just consider that this is 61 point something and this is 59 point something. So if you have 61 point something and 59 point something, the difference is not going to be of 2 greater than or equal to 2, but the difference is going to be greater than or equal to 1. Therefore, here we have 6 1. Therefore, the difference is going to be 0 point greater than or equal to 0.0001, because the difference is actually among 0.0. Okay, we can actually subtract and see. That's also quite possible. So if we just try to subtract these two things, so we have 13.4261 etc., 13.4259 etc. If we subtract these two, we see that this is 13 is common here, 42 is common, this 42 is common. Therefore, the difference is going to be something of the form 0.00. This is 61 etc. 61 etc. minus 0.0059 etc. So this difference, this is not going to be always greater than or equal to 0.0002 here, because we have to subtract from 1, we have to subtract 9, so we have to take this. So this is not going to be greater than or equal to 0.0002, but it is at least 0.0001, but this is nothing but equal to 10 raised to minus 4. Therefore, if you go back to our actual case, you can see here that if we choose like this, that is xn plus 1 greater than or equal to 1 or yn plus 1 less than or equal to 8, we will get that the difference between x minus y in this case is going to be greater than or equal to 10 raised to m minus 1. Therefore, this is greater than 0. Therefore, x is not equal to y. So there is only one possibility, that xn plus 1 greater than or equal to 1 or yn plus 1 less than or equal to 8 is not possible. So what is possible? So xn plus 1 must be equal to 0, yn plus 1 must be equal to 8. Therefore, xn plus 1 equal to 0, yn plus 1 must be equal to 9, sorry, not 8, equal to 9. So the remaining digits, we can continue like this, and the remaining digits are all going to be like that. That means all xi's will be 0 and all yi's will be equal to 9. Therefore, at the first position where the digits differ, we have xn equal to yn plus 1. All places after that, xm or xi equal to 0 and yi equal to 9. So wherever the difference happens for the first time, after that position onwards, the first number which has more positional value at the first place will be having all zeros at the remaining places, and the second number will be having all nines in the remaining places. Therefore, for all these things, the most important thing is we must be able to locate that where the change happens for the first time. If the change happens for the first time in one particular digit, from that point onwards in one of the decimal representations, everything else is 0. So that is one crucial observation. Therefore, if decimal representation starts differing at nth digit in one of the representations that xn is going to be equal to yn plus 1, xn plus 1 0, xn plus 2 0, etc. That basically means that this first representation, which has digits x1, x2, etc., that terminates at n. So there is no more going further. So yn plus 1 equal to 9, yn plus 2 equal to 9, etc. So how do the representations, different representations actually look like? Therefore, so it is going to be x1, x2, x3, etc., xn. After that 0, 0, 0, 0, etc. Now y1, y2, y3, etc. At this place xn is more, therefore this is going to be xn minus 1, 9, 9, 9, etc. So if we have two different notations, if a real number has two distinct decimal representations, they look like this. So any two different decimal representations we take, one of them must be in the form x1, x2, x3, etc., xn, and then 0, 0, 0, etc. And the other representation must be of the form y1, y2, y3, etc., and xn minus 1 at the first starting position. And so in fact we should modify it slightly. All these digits are actually the same, so we cannot even write like this. This is wrong, this is not completely correct. Instead of this, we should write here, this is not x1, this is not y1, x1, x2, x3, etc. And at this place it's differing, therefore probably we should write a little bit more clearly. So the other representation is going to be in this form, x1, x2, we will probably write here also x1, x2, xn minus 1, xn 0, 0, 0, etc., x1, x2, x3, etc., xn minus 1. After that it is going to be xn minus 1, then it's going to be 9, 9, 9, etc. These are the only two possible representations of a real number, and these two representations will occur only if one of the decimal representations terminate after a finite number of places. So the conclusion is the following. A decimal representation terminating after a finite number of digits, that is, all digits 0 after some nth digit. What is meant by terminating is after some nth digit everything is 0. A decimal representation terminating after a finite number of digits has another decimal representation. As exactly, in fact we should say as exactly one more decimal representation in the above form. So if for example we consider 1.25, then the representation 1.24999 etc. are the same, because here it is 0 afterwards, here it is 1 differing from that 5, and after that everything 9. These two representations are exactly the same. So two decimal representations will be same, provided that first decimal representation, one of the decimal representations actually terminate after a finite stage, and the second decimal representation looks like this, in this way, up to that finite position, that whatever position it's terminating. So here it is terminating at xn. So at the end position, the other representation will be having 1 less, and after that it's going to be 999 etc. Now we are going to revisit Cantor's diagonalization method. So there we took this f of 1 as 0.a11, a12, a13 etc. f2 as 0.a21, a22, a23 etc. and f3 as 0.a31, a32, a33 etc. and we chose y1 0.y1, y2, y3 etc. in open interval 0, 1, satisfying the conditions that y1 is from we also chose we also denoted the set 0, 1, 2, 3 etc. 9 to be equal to D, and we took y1 to be a member of D minus singleton a11. Here now the problem is that if it is equal to 0 or equal to 9, if a11 is 0 or 9, it can be one of the non-unique representations of a decimal of a real number. Therefore, to safely avoid that problem, correction, this is the correction. So in general, we took yi from D minus a ii. So the correction, this is not actually correct. There can be some problem with what we are doing here. So this is what we did. So instead of that, the correction is the following. Choose yi from D minus aii, not only that, it should not be equal to 0. Let us try to avoid 0. It should not be equal to 9. So since there are already 0, 1, 2, 3, etc. 10 digits and we are excluding only 3 digits, we can still have 7 more possibilities, and then 0.y1, y2, y3 will not be any fi, even in a different decimal form. Not even, in fact, not even in a different decimal form. So this completes Cantor diagonalization method.